Okay, so ready to dive in. Today we're tackling matter, what it is, how it works, the whole shebang. Think of it like your high school physical science class coming to life.
Yeah.
We're going to use, well, actually, your learning standards to guide our deep dive today.
It's funny, isn't it? I mean, we interact with matter all day long, but I don't think most people really give it a second thought.
It's true, like it's just there, right? So let's start with the basics, I guess. How do scientists even like categorize all the stuff, all the matter in the universe?
Well, think about it like this, like sorting your clothes. You've got shirts, pants, socks. Scientists categorize matter in a similar way. So you've got an element, like oxygen, the stuff we breathe, right? That's pure, one type of atom. But you mix oxygen with nitrogen and you get air, right? And that's a mixture.
Okay, makes sense. But what about all those terms?
Yeah.
Heterogeneous. What's the difference?
Good question. So a homogeneous mixture that's like a perfectly blended smoothie, can't really see the individual parts anymore, like air, for example. A heterogeneous mixture, on the other hand, that's more like a pizza. You can see all the different toppings, the cheese, the pepperoni, all kind of jumbled together.
Gotcha. So it's all about how evenly things are distributed.
Exactly.
Okay. Let's talk about something I always found pretty cool: the phases of matter. Like we all know that water can be solid ice, right? Liquid water, or steam. But why? Like, what's actually happening at a molecular level?
All right, picture a dance floor. Okay. Slow song playing, everyone swaying, barely moving, all crammed together. That's your solid. Music picks up, people start grooving, moving around, but still pretty close, right? That's your liquid. Then the DJ drops the beat, and it's a full-on mosh pit, people bouncing off each other, total chaos. That's your gas. The molecules in matter are just like those dancers. Their energy level, how much they're moving around, determines how spread out they are.
I like that. Good analogy. So
Yeah.
whether something's solid, liquid, gas depends on how much the molecules are kind of wiggling around.
Exactly. And these phase changes are physical changes, not chemical. It's still the same water, just in different forms. Like when ice melts into water, the water molecules don't change. They just rearrange themselves, move differently.
Speaking of changes, let's talk about the different properties of matter. So you've got physical properties; those are things we can observe, like color, density, or whether something is magnetic. And then you have chemical properties, right, which describe how a substance reacts with other things.
Yeah, that's right. Physical properties, it's like the substance's ID card. And chemical properties tell you how that substance interacts with the world around it. Like iron rusting. That's a chemical change because the iron's reacting with the oxygen in the air.
This might seem like a lot, but it's really important stuff. I mean, understanding these properties is the basis for like so much of modern science and technology,
Yeah.
right?
Oh, absolutely. Think about it like building a bridge. You got to understand the physical and chemical properties of all those materials you're using. Or designing a new drug, you need to know how those different chemicals are going to interact in the body.
Pretty cool stuff. All right, let's zoom in even further. Let's talk about atoms. They're the tiny building blocks of all matter, but they're not just little solid balls, right?
Nope. Atoms are made up of even tinier particles, protons, neutrons, and electrons. And the way those electrons are arranged, especially those in the outermost shell, those valence electrons, that determines how an atom behaves and how it bonds with other atoms.
So we could picture an atom like a mini solar system, right? With electrons orbiting the nucleus.
Yeah, that's a good basic model. And just like the planets in our solar system, those electrons occupy specific energy levels within the atom.
So this is where those Bohr diagrams and electron dot diagrams come in handy, right? Those visuals help us understand how the electrons are arranged.
Exactly. Think of them like blueprints showing us the structure of an atom and how it might interact with other atoms to form bonds.
Okay, I think I'm starting to get this. But then there are ions and isotopes. Those always they always kind of confuse me. What are they, and why do they matter?
All right, so ions and isotopes, those are like the special editions of atoms, right? An ion, that's an atom that's gained or lost some electrons, giving it an electrical charge. Super important in chemical reactions. I mean, think about how batteries work.
So an ion is like an atom with with an attitude, either extra negative or extra positive.
You got it. Now, isotopes. Those are atoms of the same element, but with different numbers of neutrons. So they've got the same number of protons, behave chemically the same way, but they have different masses. Some isotopes are even radioactive, which has tons of applications in medicine and energy production.
Wow, so even though atoms are tiny, there's a lot going on in there.
Oh, yeah. For sure. And that's why the periodic table is such an amazing tool. It organizes all the elements based on their atomic structure and properties, makes it easy to see patterns and predict how elements will behave. It's like a giant cheat sheet for chemists.
Speaking of the periodic table, I've always wondered why it's shaped the way it is. It's not just a random chart.
Right. The shape of the periodic table, it's all about those valence electrons we talked about. So elements in the same column, they have similar numbers of valence electrons, meaning they tend to react in similar ways.
So the periodic table isn't just a list of elements. It's like a map that shows how they're all related to each other.
Exactly. It's like a giant family portrait for all the elements in the universe. And by understanding the periodic table, we can predict all sorts of things, like which elements will form bonds, what types of bonds, and even what the resulting compounds might be like.
That's pretty incredible. So after this deep dive, I hope you all see that matter is it's way more than just stuff. It's a complex and fascinating world of atoms, molecules, and properties that shape, well, everything around us.
And the best part is, this is just the beginning, you know? The more you learn about matter, the more you realize there's so much more to discover. Just keep asking questions, stay curious, and who knows? Maybe you'll be the one to make the next big breakthrough in science.
You know what? I think I'm actually starting to like chemistry. Maybe there's hope for me yet.
There's hope for all of us.